Hello, I'm Jay Stokes, and today I'll be presenting our system called AMP, which stands for Authentication of Media via Provenance. It addresses one aspect of the problem of fake media by cryptographically ensuring that the content has not been altered since it was created or published. In particular, AMP is concerned with protecting media distributed by news organizations. In this talk, I will first give an overview of the fake media problem. Then I will define the concepts of authentication and provenance. Next, I will present the main components of the AMP system and provide a performance evaluation of AMP running as a proof of concept service in the Azure cloud. Finally, I will describe two media coalitions which use all or part of AMP to help prevent the spread of fake media. Deep fake media uses deep learning algorithms to make someone appear to say or do anything. Individuals, organizations, and governments are very concerned about the potential harm that might result from deep fake media. The problem is not just deep fakes, but also cheap fakes and content reuse. A fake video of the US Speaker of the House, Nancy Pelosi, is an example of a cheap fake where the original video was slowed down to make it appear that she was intoxicated. Another big problem is that attackers simply reuse previously published images, but in different contexts. On the right, we see the same image used in stories about fires in Brazil, Australia, California, and the Arctic. Why is this an urgent problem? Scale and accessibility. Authenticating trusted sources used to be easy. Nobody faked the New York Times or television broadcasts. When you went directly to the BBC's site using SSL, you could be sure you were getting the BBC's content. However, today, many people now get their news from social media sites such as YouTube, Facebook, Twitter, and LinkedIn. In this case, TLS only ensures that the connection to the social media site is secure. It doesn't provide any guarantees about the authenticity of the media's original source. Attackers are exploiting this loophole to upload fake media, which purports to be from a trusted news source. Three possible solutions to this problem include detection, authentication, and provenance. Detection is the ability to automatically determine if something is fake using machine learning or signal processing algorithms. While detection algorithms can work well on media from the same distribution, they struggle to detect examples from different distributions. Authentication is a process of verifying that the creator or publisher and the content of the media are valid. And provenance is the ability to determine the original source of a piece of media that helps the user make an educated decision about its trustworthiness. AMP uses both authentication and provenance to ensure the integrity of the media. Authentication is used by AMP in two ways. First, AMP uses public key infrastructure of X509, where the creator or publisher signs the media and metadata with their private key. Second, the content itself is bound to the metadata using either a single hash for images or a set of hashes for streaming media. Streaming media bindings enable low latency authentication for progressive download and adaptive bitrate streaming. In addition to authentication, AMP also uses provenance to help protect users from fake media. Provenance includes basic metadata such as who created, published, or modified the content, and when each step was done. It also provides the lineage from the original source to the end user. Recent research indicates that users rely on knowing the original source when deciding on the trustworthiness of the content they are consuming. Next, we provide an overview of the AMP system. A content provider uses the AMP authoring tools to create signed manifests and register them as part of the publication process. The manifest can either be created locally by the publisher, CDN, or social media platform, or alternatively in the AMP service itself. The AMP service records the resulting publication metadata in a manifest signed by the publisher and stored in the manifest database for fast verification. The manifest or its hash is optionally stored in a publicly verifiable ledger, and this ledger is implemented using a trusted execution environment. Finally, browsers, websites, or media players use AMP manifests and libraries for verifying the authenticity of a media item. A manifest has 4 parts. It has bindings for the media itself. It has metadata such as the title, creator's name, or creation date. If the manifest results from transcoding or one or more edits, it includes pointers to the source files. And finally, it contains a signature over this data to link it back to the publisher certificate. AMP supports 2 types of manifests, embedded and detached. Embedded manifests are stored in e-message boxes and MP4 and fragmented MP4 containers. MP4 containers contain many different boxes, including the move, moof, and MDET boxes, which store metadata and the data for the entire file and individual fragments. The manifest is distributed in an e-message box as a peer of the move box. The fragment hashes are included in e-message boxes as peers of the move boxes. Finally, a browser or social media app can authenticate the media from the embedded manifests and hashes. On the other hand, a detached manifest is stored separately in the cloud. The publisher first creates a manifest locally or using the AMP service. Next, the publisher uploads the manifest to the service, which inserts it into a database and optionally into the ledger. The ledger uses Microsoft's Confidential Consortium Framework, or CCF, which is available as open source software or as a preview service in Azure. Again, a browser or social media app can authenticate the media using the AMP service. Why is this hard? Can't you just sign the video? There are many aspects of streaming media that make this complicated. Streaming media services such as YouTube and Netflix often encode an original media file using many types of formats, and we call these streams facsimiles. Facsimiles may correspond to different codecs, compression ratios, and target screen sizes. AMP's manifest supports these different facsimiles by hashing individual chunks and storing these hashes in the manifest. This architecture allows AMP clients to be able to easily authenticate any facsimile that the user wants to view in their player or browser. A video that is streamed on the web isn't just one video. YouTube provides a good example of the different types of facsimiles that may be generated from a single video. During the publication of one original video, YouTube generates 16 separate video-only streams, 2 audio-only streams, and 3 streams which include both audio and video. Adaptive bitrate streaming poses another problem. Clients can dynamically switch streams to optimize the viewing experience due to changes in the network quality. AMP manifests are designed to support adaptive bitrate streaming to handle this problem. Facsimile hashes enable authentication for adaptive bitrate streaming when the playback resolution changes. A Merkle tree is used to speed up progressive authentication of MP4 containers. A Merkle tree is a binary tree of hashes where the leaves of the tree are the digest of the data in the moof and MDAT boxes. Each row in the tree is the hash of the data or hashes in the row beneath. The Merkle tree is encoded as 2 parts, which are distributed separately in the top-level eMessage box containing the manifest and the fragment-level eMessage boxes. The manifest as the top-level eMessage box contains one row of hashes from the tree, for example, D20 and D21. This would be sufficient to authenticate the video as long as the player can read and hash all of the data leading up to D20 or D21. But in this example, the player would have to read, chunk, and hash half of the file before authentication could begin. To avoid the need for excessive read ahead, the media can be distributed with relevant missing hashes from the tree in the fragment-level eMessage boxes, so that the player can validate the particular fragment hash is consistent with the manifest. To prove that the first sample is consistent with D20, the evidence would be D01 and D11 because these hash values can be used to form the missing parts of the tree. Controlled transformations may include transcoding by CDNs or frame resizing by social media app. To enable provenance, transformation manifests have a back pointer from the transform media to the input media that was modified. This architecture allows AMP to create a chain from the media which is being played on the phone all the way back to the original media source as long as a new manifest has been created at every step along the way. In addition to controlled transformations where the manifest for a derived media object is uploaded to the AMP service, media can undergo uncontrolled but legitimate transformations where a manifest of the transform media is not uploaded. A watermark can be used to perceptibly embed a small amount of text into the media. They can be designed to survive modest edits such as transcoding or clipping. AMP uses fragile watermarks which can be recovered by the player and provide an ID for the original media object and a URI corresponding to a service hosted by the publisher, which alternatively can be used to authenticate the media. AMP uses the public key infrastructure of X509 for its trust model. In one possible structure, a single root operated by the alliance sits at the top and issues intermediate credentials to each participating organization. Credentials could also be issued to a regional subsidiary or an individual reporter. We next provide a performance evaluation of the AMP system running in Azure. Additional measurements are provided in the paper. In this slide, we report the performance of the AMP database for 4 long YouTube videos. The database writes take tens of seconds, but are only done once for when the manifest is created and uploaded to the service. A database read is much faster and occurs once before streaming the file. This additional overhead of 300 to 400 milliseconds is small. In this slide, we provide a performance evaluation of a CCF ledger. The results include the throughput and average latency required to write an AMP entry into the ledger with 1, 3, 5, and 7 CCF replica nodes using the AMP service. We studied this within a single Azure region and across distributed Azure regions in the West Europe and East US data centers for the DC4 SKU VMs which support SGX. Finally, we measure the performance of the next generation of Azure hardware using DC8 SKU VMs, which also support SGX. In all cases, the throughput is very high, ranging from over 30,000 to almost 60,000 transactions per second, and the average latency is less than 300 milliseconds. Given these numbers, AMP can easily scale to handle a very large number of manifest uploads. In this slide, we compared the performance of our AMP system on the last row to other ledger implementations. Other ledger technologies suffer from low throughput, high latency, or both. AMP has a much higher throughput and lower latency compared to other ledger technologies. There are several coalitions that deal with media provenance, and we now describe how AMP plays a role in 2 of these. We first formed the Project Origin Coalition with the trusted international media publishers, including the BBC, the CBC, and the New York Times. All of us were working independently on provenance-based solutions at the time. We first met in January 2020 and have been working closely together since then. AMP was the original technology for Project Origin. The Content Authenticity Initiative, or CAI, was a parallel coalition led by Adobe and TruePic, which focused on image capture from the camera through the editing stages. The main scenario for AMP is complementary, including publishing, distribution, and the final viewing experience. Also, AMP primarily focuses on protecting videos, but can be applied to images as well. In February, Project Origin and CAI joined to create the Coalition for Content Provenance and Authenticity, or C2PA. The primary goal of C2PA is to produce an international standard which combines and extends the ideas of CAI and AMP to help protect the integrity of all media types. The first draft of the standard was released at the end of August and is available for public review and comments. C2PA currently has 25 members, and new organizations are continuing to join. Please consider joining C2PA if you're interested in ensuring the integrity of online content. In conclusion, authentication and provenance offer a long-term solution to some aspects of the fake media problem. AMP offers new insights to help address fake media, and all data structures are included in the extended archive version of this paper. Version 0.7 of the C2PA standard is now available for public review. Please offer feedback on the draft. This slide provides some of the references we used during the talk. Thank you for your attention.